Everyone hates physics, right?
Yeah.
I'm a physics HL student, so I can tell you from experience that we also hate physics most of the time. So why would anyone want to know anything about quantum communication and quantum physics? Well, I had the great opportunity to work during my summer and winter holidays as an intern at University of Nicolaus Copernicus in Toronto. I worked in the laboratories of atomic, molecular, and optic physics. And I had the great opportunity to see a lot of the projects that the single photon laboratories are working on right now. And I can tell you, it's more fun and interesting than it sounds. So, why should we talk about quantum communication? Well, it's because we are right now in the age of the great inventions of the quantum age. You probably think about those great big technologies like the Hadron Collider that you probably will never see in your life. However, most of us go to opticians. And right now, physicists are working on finding new technology that can be used to shoot one single photon into your eyeball to measure more appropriately the size of your eyeball and find you better glasses. But I didn't work with optical part of it. I worked with the quantum communication, and this is what I want to introduce to you today. So, everyone has computers, right? We know them, we love them, great things they are. We use them to mostly communicate. We talk to our parents, we keep the pictures of our blackout bodies for blackmail. It's a lot of fun. This is data. So, there is a small, big problem with data, but let's take a look at it. We have a piece of data, right? It's a picture of me from a party. It's cropped so no one else is there. But this is our piece of data. Who has access to it? Well, obviously I have access to it. I use it. My family and friends that I send it to. But also some app on my laptop, a Trojan I accidentally got, and some other third party that I do not want to have access to it. So this is the problem with data. Anyone can have access to it. So if you talk to your mom and you get the secret family cookie recipe, they can actually become freely available if anyone gets in. People much smarter have decided to solve this problem, with quantum physics, of course. So, for that, we will probably need quantum computers. We don't have them yet. We don't really know how to make them yet either, but we have theory. And believe it or not, we do have tons of theory on it that has been proven to work. So, let's start with the basics. Photons. Photons are those little light things you probably heard about. They are used for many, many things, like seeing, for example. But in this case, we'll use them to carry information. We will need an entangled photon pair, big words, and we get it through something called spontaneous parametric down conversion. Big words, easy concepts, don't worry. It's a process that usually takes place in laboratories. We use a photon pump to go through a non-linear crystal, and then from the crystal emerges a pair of entangled photons. And we are not at the lab, but we can actually do this experiment at home using olive oil and a green laser. If you look at the picture, when the laser goes into the oil, it changes its color to red. Well, why does it happen and how do we know it? Well, the photon is broken down into two. And because we are breaking the photon into two, we also need to split its energy. This also means a change in the wavelength due to physics reasons, but it basically means that the color will also change. The thing with entangled photons is that they have something called polarization. One of them will come out being vertical, and if one is vertical, the other is horizontal. Or if one is horizontal, the other one is vertical. It's like those cliches in movies. Like, you probably also know those people in real life. Like, they are complete opposites of each other. They can't agree on anything, they are attached at the hip. But why do we need those? Well, because quantum communication is like a game of matching. So in here, let's see our instructions. We have the horizontally polarized photon, we have the vertical one, and then we can also use special polarizers to change the polarization to half horizontal, half vertical. And then we also have our bases. Well, that sounds complicated, right? Not really, because this is what it actually is. A simple game of matching shapes to go through the holes. Well, you see, this is actually what we're going to do. Because our photons will be shot into the bases, and if they fit, we'll be able to get a reading of them. If they don't fit, it's a bit like smashing the square block into the triangle hole. If you force it really hard, it will go through, but it will be deformed. So let's see. If it goes through, it means that we are able to get a proper reading of it. It will become either a 0 or a 1. But if it falls down, it means that the photon goes meddled with, and we can't really read it well. So let's see, in our first base, the vertical went through, but it won't go through the second one. And the same will happen with other photon polarization. Each one of them has to come out of the base in some way, but it's not always a good way. But how are we going to use it? Well, in quantum communications, we usually talk about Alice and Bob. Alice wants to communicate with Bob. The easiest way for them to communicate with each other is to use one base. If they both use base 1, they can both send horizontal and vertical photons and get the lines of 1 and zeros. Alice will know the polarization of the photons because she measures one of the photons from the entangled pair. Bob will get the other one. This means that since we always know the polarization of the other photon, no matter how far they are apart due to the entanglement, both Alice and Bob will know the results. But what is not so perfect? As you can see, this is easy and nice, right? They flow in, they are able to read it. However, like we talked before, our data is usually spied on. So here is where Eve comes in. Eve is an eavesdropper. She wants to get the data that Alice sends to Bob. So if she takes an incredibly good guess and chooses the same base as Alice and Bob, she will be able to read the photons without deshaping them. And Alice and Bob will not know that something was spying on them. We don't really want that, do we? Like, those cookies are too good to be free, okay guys? So, this is where the BB84 protocol comes in. It's a protocol that physicists have come up with, and it basically means that Alice will choose a random base to send photons in, and Bob will also use a random base to measure them in. Eve also has to guess the bases, so it's basically a lot of gambling in here. Like, let's see, some photons will fall straight from Eve because they got misshapen. The polarization is not the same. Some will go through just fine. Some will go through Eve without change, but Bob will not be able to read them because he chose the wrong base. So how do we solve this problem? Well, it was actually a bit of an issue for a long time in physics. However, the physicists have decided that the best way to solve it is for Alice to call Bob on the telephone and tell him the key. Well, how do we give the key so it's secure? We can tell the photon polarization or just a line of 1 and 0s. But that doesn't really work. If Eve is still listening to us on the phone, she can figure those out. However, if Alice shares bases that she used, it's not as easy to figure out. Then what is happening is Alice and Bob take their sets of data and compare their guesses. If they guess both correctly, they keep the data. If they didn't, they get rid of it. In this case, in this scenario, Bob will probably, most likely due to mathematics, guess around 50% of the time correctly. This information does not help Eve, because if she guessed the same as Alice, but Bob did not guess, it doesn't help her, because they get rid of the result. If Alice and Bob and Eve guess all correctly, the information is kept. However, Eve does not have enough information to actually get the data. This is an incredibly interesting topic that is still being worked on and scientists are trying to improve it. Right now, the BD84 protocol has been tested and proven successful on short range. However, we are still very far away from using it in everyday life. I decided to present it to you because I think that it's a great way to see physics in a bit of a different light. Physics is not only counting how much someone weighs on the moon or how fast we will go in a circle. However, it can also be used in real-life applications. So one day, maybe you will be able to send the family cookie recipes to your kids without having to worry about any pesky eavesdroppers. Thank you.